Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. This week, I chat with Bobbin Threadbare, the lead at Miden, a project recently acquired by Polygon. We start with a quick Starks versus Snarks 101, and then we take a journey through Bobbin's early work on open source Stark libraries, how he learned Starks and learned Rust, all the way up to the project that he works on today. That is Miden, a Stark-based ZK rollup, which is an evolution of his earlier work on Distaff VM and Winterfell. Winterfell being a highly performant Stark prover developed at Facebook's Novi. This is a very ZK-heavy episode, and I hope you'll enjoy it. Before we start in, I do want to let you know that it's the last chance to donate to the Zero Knowledge Podcast Gitcoin grant during this Gitcoin CLR matching round. It ends, I believe, tomorrow. So yeah, if you want to donate, this would be a great time to do it. There is also a dedicated side round focused on zero knowledge right now, so be sure to check that out as well. I also want to thank this week's sponsor, Aztec. Aztec aims to be the privacy layer for Ethereum. They believe that unlocking programmable privacy is the next frontier for blockchains. Aztec is the first zero-knowledge rollup built from the ground up for anonymous payments and DeFi transactions. Join the thousands of users already sending funds privately on ZK Money. That's zk.money. And start interacting with Aztec today. So thank you again, Aztec. Now here is my interview with Bobbin Threadbare. So today I'm here with Bobbin Threadbare, who's the lead at the Miden project, a project recently acquired by Polygon. He's also the author of Distaff VM and Winterfell. So welcome to the show, Bobbin.
Thank you, Anna. Thank you for having me.
So Bobbin, we met back in September, October 2019. I remember you were speaking at a Starkware conference, and I immediately knew that you were a Stark guy. I know that the projects and work that you've done since then are very Stark focused. I want to start this interview by actually getting a little sense for you pre-ZK. What were you up to? Kind of what led you to get into this, and maybe where did you enter the space?
Yeah, definitely. So I actually entered the space relatively recently. I would say it was summer of 2018 when I really got into crypto. I've known about Bitcoin and Ethereum, way before, and kind of was passively observing what's going on, but really actively got involved in 2018, kind of started thinking about cryptography. And, when I say actively got involved, I actually started to learn about cryptography and trying to think through all the kind of math aspects of it and kind of more structural things that are needed in blockchains and things like that. So before that, I actually was running a small startup. It was kind of like not a crypto-focused startup. It was just a regular web company focused on trying to figure out how you can maintain a personal reputation across different services and sites. And it was a very centralized product. And I didn't like the aspect of that where basically all your reputation data is being stored in a single server. So one of the kind of motivations for me to learn crypto was figure out how can we make it decentralized. And as I learned more about crypto, I got really interested in zero-knowledge proofs, and specifically this general computational integrity proofs, which are Snarks and Starks, because for whatever reason, it was immediately clear to me that this is something that is really needed in blockchains, because the promise is that you can verify a computation and then nobody else needs to rerun the computation. And in blockchains, basically every node has to re-execute the same transactions, and it just seems wasteful to me. So it was very clear to me that this technology, ZK, is something that is kind of natively needed in blockchains because it allows you not to re-execute the same piece of code on millions of machines.
Yeah. Would you say that you started in, though, on the Stark front, or were you kind of generally exploring zero knowledge at this time?
I would say I started even more broadly on the crypto side, try to learn about elliptic curves. So I'm a software engineer by training, and I don't have any cryptography background. I'm not a math PhD or crypto PhD or anything of that sort. So it was all very new to me. So I started to learn about elliptic curves, kind of other cryptographic primitives, and trying to understand how they fit into different protocols like, signatures and how hashing works and all of that stuff. So that was something that I learned throughout, basically starting from summer 2018 onward. And I would say by early 2019, I got to zero knowledge. And that's where it really clicked for me that this is really exciting and almost, borderline magical technology. And I didn't go right for the Snarks. I kind of read a few things about Snarks and Starks, but for whatever reason, I think Starks resonated much more with me than Snarks did. And I usually explain this as in my mind, and I think many people might disagree, but Starks is simpler to understand. There is very few foundational things that you need to have. You don't need to understand, for example, how elliptic curves work to be able to reason about how Starks work. So there is no need for a lot of advanced crypto that is needed for most other Snarks, like elliptic curves and pairings and all of that stuff. And yes, you can treat, I think, those as black boxes and still understand how the basic stuff works. But for me, it was much easier. Basically, I know that even with Starks, there is a lot of different layers and a lot of theoretical complexity, but at least kind of the core mechanism was much more immediately clear to me. That was one of the reasons why I kind of gravitated towards Starks.
Something that I feel we've definitely done on the show before, but I'd kind of like to do again today is make that distinction between Starks and Snarks. So I think I've often highlighted what the resulting differences are, like how it appears, but maybe you can give us a little bit of insight into what those differences are kind of under the hood.
Yeah, definitely. Well, one thing I should probably say up front is that I think the terminology is getting blurred more and more, and it's kind of not always clear what you should call a Stark and what is a Snark, because I think people use them in different contexts, and there is a more kind of formal mathematical definition that, some people argue about what exactly should be called a Snark or a Stark. But, going back when they started, at the time when kind of Starks came about, Snarks existed in this kind of paradigm where you had to have a trusted setup. So one of the things that Starks promised was the absence of a trusted setup. So transparency is something that is what the T in Starks stands for. So you don't need a trusted setup. This is not the case anymore. There's other proving systems right now that do not require trusted setup. An example would be Halo, for example, doesn't require trusted setup. The other distinction between kind of a very fundamental difference between Starks at the time and Snarks is that the arithmetization used. So Snarks at the time relied on R1CS, and R1CS is still probably one of the more popular ways to describe computations for this proof of computational integrity. But Starks had this different type of arithmetization called AIR, and that is a very different thing. Nowadays, there is again a bit more blurring of the lines that is happening because Plonkish arithmetization is also kind of closer to AIR. You can even say it's randomized AIR with pre-processing and things like that. So there is actually more similarities now, but there is still quite a few differences. So I would say for the most part, Starks rely on very few cryptographic assumptions. So basically from the cryptography side, you only need to have hash functions for Starks. For Snarks, you still need to rely on elliptic curves, and sometimes it could be pairing-friendly elliptic curves. Other times it could be just regular elliptic curves, but there is still a need to rely on kind of more advanced cryptography. And that also, potentially makes Snarks vulnerable to quantum computers. So one of the benefits of Starks is that they're resistant to potential, future quantum attacks.
Totally.
Because they require very little kind of underlying cryptography. The other distinction, which is, I think it depends how you interpret it, but basically Starks say that they're fully transparent and they don't require any pre-processing, which is, a verifier just needs to know the AIR description and that's it, and they can verify any proof. While Snarks frequently, require some level of pre-processing, that, there is. The distinction is that besides verifier and approver, there is also this indexer that runs and pre-processes the circuit or something beforehand so that the verifier can evaluate it succinctly or verify it succinctly. So there are those distinctions that I think are still relevant. I actually have this diagram in my mind where there's two circles, Snarks and Starks, and they overlap. And basically anything that is non-interactive and transparent and kind of scalable, this is kind of falls into this intersection of two circles.
I see.
And that could be, scalable, transparent Snarks are Starks, and then non-interactive Starks are Snarks as well. So it's kind of there's an intersection between them.
Let's talk a little bit about the kind of outcome of these two systems. So maybe we can start with looking at the proof size. How are they different?
So the proof sizes, specifically how big of a proof that gets generated by the prover and how much you need to send to the verifier, is definitely bigger for Snarks, but I would say to give like a common benchmark is that Snarks like Growth 16 and Plonk, the proof sizes are tiny. They could be 200 bytes or maybe half a kilobyte or something like that. So they're really, really small. For Snarks, even for simplest computations, we're looking at maybe like a dozen kilobytes. And then for, more useful computations that we frequently need to encode like some circuit that does verification of a transaction, for example, the proof sizes are in dozens of kilobytes, 80 kilobytes, potentially closer to 100 or something like that. So, rough ballpark. It's very computation dependent and also depends on the security level that you want. But basically, Snark proofs are at least an order of magnitude larger than Snark proofs, and in some situations could be like 2 orders of magnitude larger.
Got it.
But I would say this comes with this is not necessarily the inherent property of Snarks, but it comes with a kind of this need to rely only on very few cryptographic assumptions. So if you only rely on hash functions, your proof sizes will have to be fairly large. As soon as you can rely on elliptic curves, you can bring the proof sizes down dramatically. But then you lose like post-quantum security, for example. So your proofs are no longer post-quantum secure. So in theory, you could build a Snark that is kind of using, you probably heard the term Fry as something that is used in Snarks, but you can use some other polynomial commitment into the Fry, or you could instantiate Fry to be done using an elliptic curve rather than hash functions. And in that case, your proof sizes will go down dramatically. But then, yes, you do give up. First, you give up the post-quantum security. And second, your prover speed is going to increase significantly. So the proof speeds, when you need to rely only on hash functions, for Snarks especially, proving speed is very good. They're very fast. Again, there is a lot of nuance in that. It depends on the type of computation that you are generating a proof for. But for a lot of computations that we do care about, Snarks are very, very fast. But as soon as you need to rely on elliptic curves, you kind of lose some of the speed advantage as well.
When it comes to the verification sizes, is this calculated in time spent on verifying, or is there like we're talking about proof size, but is it also is it verification time?
So there are two aspects to it. There is the proof size itself, which obviously the larger proof, you incur a little bit of penalty, but there is also a verifier time that it takes to verify the proof. So for Snarks, even though the proofs are very large compared to other systems, the verification time is fairly small.
Yes.
Because again, you're only evaluating hash functions, which are very fast on modern computers. I think the verification time between Snarks and let's say Growth 16 and Plonk are fairly comparable. They're not hugely different. But as an example, Bulletproofs is another system. It has a very relatively small proof sizes, under a kilobyte, or maybe depends on, again, what you want to verify, maybe slightly over a kilobyte. But then the verification time could be significant because it really depends on how big of a computation you try to generate a proof for. So the verification time for Bulletproofs is linear in the kind of complexity of the original computation. Which is not the case for Snarks and Snarks, where this verification time is logarithmic. So there are these two aspects, the proof size and the verification time. And Snarks do fairly well on all metrics except for the proof size.
Got it. But I guess, have you also seen a lot of development in that? The fact that there's this overlap and techniques have been shared between these two systems. Do you think is that proof size actually shrinking? Or do you think have we hit the smallest it can be for now?
I think the proof size for Snarks, you can't reduce it much more without giving up something. So it will stay in dozens of kilobytes unless you give up one of the things. And what I mentioned, for example, you can give up post-quantum security, or you can start losing elliptic curves, and then you can shrink down the size, probably by a factor of 10 or something like that. But without giving up that post-quantum security, or maybe something else like prover speed, it's very difficult to shrink the size. I don't want to say it's impossible, because I don't think I have enough of theoretical background to say that nothing can be done to do it. But at least as far as I'm aware, there is no known or kind of even promising technique to reduce the Snarks proof sizes significantly without giving something up that kind of forms the core promise of what Snarks are. But I do want to say that I think the proof sizes are, I think a lot of weight is being given to the proof sizes, but I think for the computations that we care about in a blockchain context, proof sizes are not necessarily that important, especially if you can do recursion. So if you can, I haven't seen the recursive Snarks yet, but this is something definitely that I'm hoping to build in sometime in the future. But as soon as you have recursive Starks, the proof size becomes much, much less of an issue because,
Totally.
you can take 1,000 proofs and generate a recursive proof of verifying all of these 1,000 proofs, and you shrink the size of that one proof significantly. So I do not think that, I think at this point, maybe the proof sizes are somewhat of a disadvantage for Starks, but it's not a fundamental disadvantage. I think in the future, we should care about proof sizes much less.
And when you say the word recursive, just for our audience, that means kind of like taking a snark and then making a snark out of that snark. That's usually how we hear about it, recursive snarks, right? Sort of like snarkifying snarks, as Isaac from Mina would call it. But when you talk about recursive Starks, is it the same concept that you're like taking multiple Stark proofs and then you're potentially creating an overarching Stark that combines that?
Yeah, that's exactly the concept where, you have many proofs, and you just, instead of a verifier having to verify this thousands of proofs potentially individually, you can verify single. There is another layer of Stark proofs, which aggregates all of these proofs together, and then you have just a single proof. So,
Cool.
you go from 1,000 proofs, 80 kilobytes each, to a single proof, let's say 100 kilobytes, and that's it.
Nice. And so I guess it could be said that you're Starkifying Starks, but I don't know if anyone's going to use that.
Yes.
So I think this gives us a pretty good picture of what the Stark is, also in comparison to Snark, something we've covered a lot. But let's go now into the projects that you've built using Starks or around Starks or for Starks. So when we met, you were working on something called Gen Stark. Like, what was that? What was that project?
This was actually the first project that I started working on in zero knowledge space.
Okay.
And the way I got to work on this project is actually very interesting because, as I mentioned, I was doing this research for my other startup, and, my other startup wasn't doing that well. So I kind of decided to sink more time into this and just really learn about, as soon as I figured out what Snarks and Starks were, I really wanted to kind of like understand them deeply and see how they could be leveraged even outside of the startup that I was working on. And, as I mentioned earlier, Starks resonated more with me, in part because I thought it was simpler and it kind of like made immediate sense to me how at least the basics of the underlying mechanics work. But also I thought, and I know a lot of people will disagree, but I think Starks are more future-proof because, if we're going to have quantum computers in 10 or 15 years, and if I'm going to spend next X number of years learning something, might as well spend it on something
advanced.
that will... Yeah. Exactly.
Yeah.
So there was very limited resources out there at the time about how you can learn about Stark. So to be honest, there was some posts from Stark where there was the blog series from Vitalik. So I kind of like went through it. And I think one of the things that was immediately useful to me is the Vitalik's tutorial on Starks, because it actually had some Python code attached to it. And I can read code, so it was easier. So for me, the way I learn personally is I try to like build something. I learn by building. So I was like, okay, I'm going to just rewrite this tutorial using a different language. So at the time it was JavaScript, which looking in retrospect is a horrible language to write Starks in because it's very, not performant. And you get very slow proving speeds and all of that stuff. But, that's what I chose. So I basically started out by rewriting that tutorial in JavaScript. And as I was writing it, I first of all, I understood how the internal mechanics work, but also the tutorial was very specific for one type of computation. And I saw the opportunities how you can make it, work more useful, where you can take it as a library and, try to generate Stark proofs for other computations. So I started to generalize it to something that is not tied to a very specific circuit, so to say, or a specific computation. And that's what Gen Stark was. That was the kind of general purpose Stark prover, which you could provide, you can verify any type of computation with. And that's what I think I shared this kind of like the early version of this on ETH Research at some point. And to be honest, the response was incredible. So like a few people reached out, Vitalik reached out to me, a few other people from the community reached out and asked, offered support and help and work on that. And Starkware guys reached out and, invited me to that conference where we met. It was very, very, I would say, encouraging to see such level of response and support. And I kept working on this library. But then I kind of like, in my kind of thinking, even the library itself was very difficult to use. So that led me to try to think, okay, how can I make it simpler? And that what led me to like thinking about like AirScript and AirAssembly languages, which the idea was that it's how do we make it simpler for regular developers to write Stark proofs?
We actually have a video, like there is a video recording of like you giving a talk on AirScript that I'll link to in the show notes. I know you did just mention air arithmetization, but I don't know if we really dug into that. Like the name air, what does it actually mean? What is it actually doing?
Yep. So AIR is basically, it's an acronym for algebraic intermediate representation.
Okay.
And it is the way that you describe computation so that the start proving system can understand it. And just to take a step back, there is, if we think about programs that we want to prove execution of using Snarks or Starks, we can just take a source code of the program and run it directly through the proving system. There is this step that is called arithmetization that basically takes a program as written in some language, let's say C or Rust or, JavaScript or whatever. And we need to describe it using kind of like a set of polynomial equations. And this is the step called arithmetization. And Snarks use arithmetization that is called R1CS that basically takes a computation and describes it as an arithmetic circuit. And Snarks use this AIR arithmetization that takes a computation and describes it as, intermediate algebraic representation.
Is it somewhat like the opposite of what a compiler is doing? Are you going the opposite way, or would it be some sort of compiler? It's a translator, I guess, right?
It is a translator, yeah, but it is not going the opposite way. It's not generalizing, I think, the original code, but it is kind of evaluating the structure of the code. And, in all honesty, this compiler is usually, at least in a case of AIR, is very frequently a human who is trying to take the computation and describe it in using polynomials. And that's, by the way, one of the complexities of Starks is that it's not trivial of how you take a computation and transform it into AIR. There is quite a bit of complexity associated with it. And that's one of the reasons, for example, and I think we'll talk about this later, is that people are working on virtual machines where you only have to write AIR once, and then you don't have, you can generate any start proof on that virtual machine, but the AIR part is only developed once rather than for each specific computation.
Okay.
For Snarks, the computation is called R1CS, and it's, in many ways it's simpler because it's easier to compose different R1CS circuits, so to say. The technique of how you can translate a program into R1CS is also, can be automated to a higher degree, I think, than you can do it with AIR. So there is quite a few libraries out there that have gadgets for R1CS. There are very few, or if any, libraries out there that have gadgets for AIR because, again, composability of AIR directly is very difficult. So there are pluses and minuses, and I think that's why a lot of people kind of gravitate toward R1CS and other Snarks as opposed to Snarks because of the complexities of arithmetization. But hopefully, with advent of these virtual machines, this is not going to be an issue.
Yeah. It's almost like, do you feel like you're building the foundation so that people can start using this stuff without needing to be in the weeds? Or are you creating a framework that they can easily make these decisions for how to do it and do it correctly?
I think even from the time when I started to work on GenStark, my kind of end goal was how do I make it so that you don't need to understand cryptography or you don't need to know anything about zero knowledge proofs to be able to generate Stark proofs. So I think we're getting to the point, we're not 100% there yet, but we're getting very close to the point where you don't need to be a cryptographer or you don't need to really understand Starks to be able to use them. I think the tools that I've tried to build, starting with GenStark and then AirScript and AirAssembly, and then Distaff VM, that was the next evolution of kind of my journey, was kind of trying to make it progressively reduce the burden of you having to understand cryptography. And that is the goal.
And I guess that actually leads us to your next project, which was Distaff VM. Tell me how somebody would actually interact with this. So we've talked about VMs before, virtual machines on the show before, usually in the context of EVM. That's the one we say the most. But what is Distaff VM?
So Distaff VM, I think, was, because it's now superseded by a different VM, but which we'll talk about later. But it's basically a virtual machine in where there are a lot of other virtual machines. You mentioned EVM as another example, but it's a virtual machine that has its own assembly language, and you can write programs for that virtual machine in this assembly language. And this is, regular assembly language. You don't need to understand anything about cryptography to write programs for Distaff VM. And the advantage of Distaff VM was that for any program that you write, it automatically generates a Stark proof. So it kind of does the translation automatically for you. You don't need to think about how do I need to express my program as air. The VM has its own air, and it is able to execute the program that you write and generate a proof for your computation without needing to generate new air for it. That's the biggest advantage. I think to give a little bit of context about how Distaff VM even came about is that, I was working on those air script and air assembly languages, and, I spent quite a bit of time, probably close to half a year working on them. And I got to some point, but it wasn't satisfactory at all. It was still very complicated. A person who've never seen Starks or understood how they work still would have a fairly high learning curve before they would be able to use any of those languages. And that led me to think about what is the better way. And the better way in my mind was building this VM. But at the time when I started working on it, I actually didn't think, anything useful will come out of it. It's like the story or the journey that I went through is very similar. I think you had Zcash people here on the podcast, which described how they came up with Halo, where they started with something that they didn't think was practical.
Yeah. It was in the implementation. It was like as they were building it in, they found this like secret, something researchers had kind of missed. It was interesting.
I wouldn't say that I found the secret, but like basically I started working on this VM without thinking it would be very useful or powerful. So like, I knew some simple techniques that could make it work. Maybe I thought, it would be very limited. And as I was working on it, I discovered that, well, I think I can now handle if statements. I know how to do if statements. And then I built if statements. And then I was like, okay, now I think I know how to do loops as well. So, and then, and then I worked on some more, and I think I know how to do random access memory. And basically, over a course, I would say of like 4 or 5 months, it went from just a toy project that I basically didn't think was going to be useful for anything to something that I now think can support Turing-complete computations and basically is a general purpose VM. But that I didn't start out trying to think, okay, I'm going to build a Turing-complete virtual machine. It was more kind of like, okay, let me experiment and see how things work out.
In that era, though, like, was AirScript the language to write on the Distaff VM? Like, basically, I'm curious if there was a DSL in there, if you had a domain-specific language for this, or you're using something else.
So there was a DSL, but it wasn't AirScript. So the way to think about this is that Distaff VM supersedes AirScript. So AirScript was my earlier attempt of how you make Starks accessible, but it didn't succeed as much as I would like it to have succeeded. Okay. So Distaff was kind of like starting from a blank slate. It did have a kind of domain-specific language that's called Distaff assembly, basically, which is the assembly language of the VM itself. But yeah, it's basically, you don't need AirScript if you want to use Distaff VM.
Got it. It sort of covers it up. Like we're leaving AirScript in the past. We're moving forward.
Right.
And now I want to push forward because I know like Distaff VM's also like midway through the journey, I guess. Maybe. Yes. Maybe not. Maybe it's still even beginning. So let's talk about what you did next. I'm going to let you tell that story because I know kind of what came out of it, but I don't know what iterations happened in there.
Yeah, so actually, Distaff VM is still, or was still like a, research type of project. And there were a few things that, I wanted to improve. Like, first of all, it wasn't feature complete, but more importantly, like the underlying proving system, I thought could be improved significantly. So it wasn't a very high performance system for generating Stark proofs. So actually, halfway, I would say, I kind of put Distaff VM aside for a little bit, and I joined Facebook as part of their research group. And in there, I got the opportunity to work on a lot of zero-knowledge tech and Starks as well. I think overall, the outcome of this was the Winterfell project, which is kind of a underlying, like basically a very high performance and capable Stark prover. And, up to the protocol itself is much better implemented as compared to Distaff. And I worked on it over a course of probably like 8 months or so at Facebook and had a lot of help. Actually, my experience working in Facebook in the crypto group was extremely positive, but I basically was able to collaborate with extremely bright people there, and they helped me a lot. I as I mentioned, I'm not a cryptographer, so I was able to rely on more kind of a theoretical expertise of people who work there. And it was very interesting. The environment was very collaborative and very open. I think I'm grateful a lot to be able to kind of have chosen my project more or less freely at the time, and being able to work on Winterfell. But at the end, so we built Winterfell. This is a Stark prover, and the idea now is that we can swap it for the prover that was in the Distaff VM to make Distaff VM and actually the new iteration of Distaff VM much more powerful. So you can rely on this much more advanced prover.
I see. So Winterfell is like a component within this VM model that you were already building.
Exactly.
Okay. And it's making the prover more efficient? Is it making the proof smaller, or is it making the proof creation faster, or what is it doing?
Yep. So it's doing a lot of those things. But I think the way to think about Winterfell is that you still need to bring your own air to describe it. So it is still at the level of abstraction that is not as developer friendly as Distaff, for example, is.
Okay.
So you need to still understand Starks, you need to still understand air, you still need to be able to describe the constraints yourself. But you can describe any constraints on Winterfell, and it's a general purpose Stark prover. So it's very similar to what I was trying to do with GenStark in JavaScript, but it's now done in Rust. It's now done in a way where it can run in multiple threads, so it generates proofs much faster. The implementation of the Stark protocol, as I mentioned, is also up to date, to at least to what I am aware of. So the proofs are smaller compared to like the proofs that were generated by GenStark or Distaff VM. They're still in dozens of kilobytes, but roughly half the size of what it used to be with the old provers.
Very cool. What was Distaff VM written in originally? Like, did you have to rewrite anything for it to work with this with Winterfell, which was in Rust?
So Distaff VM was also written in Rust, but
it was, okay.
I should say that was my first project in Rust. So I was still learning Rust as I was writing Distaff VM.
I love how so many of these like so iterative. It's like your learning project is also like eventually powering these like really powerful things. That's cool.
Yes, I think. I mean, again, this is how I learned by doing. So for me, I was like, okay, I should learn Rust. What's the best way to do it?
So did you have to go back and like rewrite any of this, or did you get sort of collaboration from, I don't know, any of your colleagues in doing this?
Yeah, so even though Distaff VM was written in Rust, we basically rewrote the prover for Winterfell from scratch. I mean, it started the core started by copying some of the Distaff underlying components, but at this point, it's unrecognizable. So much has changed, in part because, I can code in Rust better, in part because I also understand Stark protocol much more deeply now. So it's kind of a journey where any subsequent piece of code is much better than the previous one.
Cool.
Winterfell, even though it started out as kind of core Distaff prover, it's very, very different. And now, I think we'll talk about it later, but the next iteration of Distaff VM, which is called Miden VM, is using Winterfell as its component, but it's also taking some parts of the Distaff. So over the last few months, I actually released the release of Miden VM 0.1 is basically migrating original Distaff VM to use Winterfell as the backend prover. So now this is what Miden VM 0.1 is. Very
cool. And this works. This is what I wanted to talk about next anyway. I felt like that was going to be the following. So Miden is the project. And would you say Miden is Distaff VM rewritten around Winterfell? Like it's basically like in that process where you kind of were going back and rewriting some of this stuff, it just sort of, it did shift. It changed enough that you felt like it was actually a new product?
It is a new product now, but it is even going to be a newer product in a few months from now, because at this point, basically the Miden VM 0.1 is just the Distaff VM using Winterfell prover, which makes it more efficient, faster proofs, smaller proof sizes. But the functionality of the VM is still the same as Distaff. You still have the same kind of relatively limited instruction set that, it still doesn't have random access memory because I never got around to implementing actual random access memory. But at the same time, over this year that I was working on Winterfell and other things at Facebook, I've realized that there could be a lot of improvements done to the VM itself to make the instruction set more useful, to add random access memory, to adapt it to, I would say, a blockchain environment where, you could prove solidity programs using Miden, for example. So what I'm very actively working on now is developing this new version of Miden VM, which will be even more developer friendly. And I can talk a bit more about what I mean by that, but it will basically support languages such as Solidity and other high-level languages, and will be specifically tailored to blockchain work. And Miden VM itself is a part of a bigger project, which we can, I guess, talk about in a few minutes.
Yeah, I mean, I think we need to now mention some big news that happened recently, and then we can maybe dig a little bit deeper into what kind of the plans are for Miden. But yeah, so I think it was a few weeks ago, maybe a month ago, that we heard that actually, someone who had worked on Winterfell was joining Polygon. That was the way that this kind of came across. So yeah, tell us a little bit about this move and what this means for Miden.
Yeah, so at Facebook, I worked on Winterfell, but one of the things that I still really wanted to do is kind of make this kind of transition to build or develop Distaff VM further. And while there, I got approached by Polygon guys, and they talked to me about kind of their vision of how they want to evolve Polygon suite of solutions and things like that. And, it made a lot of sense to me. I think it is fairly clear right now that they're betting very heavily on ZK tech, and there are a number of kind of different solutions already being developed. And Mikhailo from Polygon knew about Distaff VM even way back when I was working on it. He didn't know about me working at Facebook because Bobbin actually is not my real name, so I work under different names in different places, I guess.
That's fair. I only know you as Bobbin.
Yes.
I'm going with that name.
Yeah, so basically, like the reason why people didn't hear about me for a year because I was working under a different name, and Winterfell was released under a different name as well. And then, I talked to him about my work on Winterfell and like what I would think about the next evolution of Distaff VM. And I think it fit well into their view of how they want to approach this strategically. So I got the opportunity to come and work to Polygon to kind of make Distaff VM a much more powerful VM and build a layer 2 solution, a rollup around it as well. So there was a name change from Distaff to Miden, kind of to signify that this new VM is going to be much, much more powerful. And, there is a lot of new things that I think justify the name change. And it is, as I mentioned, going to be just one component of the overall. So once the VM is built, or at least is in a stage where it is powerful enough to support the types of computations that I needed to build a rollup or a general purpose rollup, there will be work starting around trying to make this into a layer 2 solution that can execute arbitrary smart contracts and generate Stark proofs for them.
Very cool. Does this have any sort of echoes of ZK EVMs? Like when here you're talking about a VM in itself, so you can actually do quite a lot. There's like a Stark that's going to act sort of as the connector, I guess, to the L1 between like an L2 and an L1. Yeah, like because we had Jordy on the show. Jordy Hermes, also a company that's now part of the Polygon family. And there we had talked about the ZK EVM idea. So would you put that in a similar category, or is it a different VM? Like, does it not actually interact the same way the L1 would?
So it is a different VM, but I think kind of the overall goal is, I would say, similar. It's just the route to that goal is, for example, for Jordy and for Miden is different. I think at this point in time, there are quite a few projects out there that are building different types of zero-knowledge virtual machines. There is, you mentioned Hermes and Jordy. There is Starkware with Cairo. There is ZK Sync with, I think they call it ZK EVM or something like that. And I think there is 2 or 3 other projects that are trying to build virtual machines that are automatically generating zero-knowledge proofs. It seems like this is the way, at least in a lot of people's mind, to forward in terms of how you can support very organically zero-knowledge proofs on in the blockchain world. So this virtual machines all make different trade-offs and different design choices. And I think there's pluses and minuses to those choices. And I think the space is very early in terms of figuring out, which set of those choices is the correct or maybe appropriate for a given use case. To compare with Jordy's approach that you mentioned. So Jordy's building a very close to EVM replication of the VM.
Exactly. We talked about it. Like opcodes will be the same. Yep. And I remember it was something like you take let me see if I do this right, but I think you take a Stark-like construction and then you snarkify that and then you write it on chain. So there's actually this combo.
Yep. I mean, those are very valid design choices. There is a reason why you would want to do that, let's say, support EVM at the opcode level, because it will make it much easier for people to migrate smart contracts. Miden VM takes a slightly different approach. So there is a VM that is different from EVM. There is going to be its own assembly language that has its own opcodes. But the idea is that it will be powerful enough for you to be able to compile Solidity into it so that you can't migrate a smart contract basically at the bytecode level, but you can migrate it at the Solidity level. So it may be a bit more involved in terms of migration, but there are other pluses and minuses that it offers. One of the benefits, for example, is that I'm really interested in is supporting other languages besides Solidity in Miden, so you can potentially have a safer language or something that prevents, has more rigorous static analysis or something like that, potentially could eliminate some bugs and things like that.
Interesting. What do you kind of imagine, like if the two projects, and I feel like it's not the only one for Polygon, but I know that things maybe haven't been announced yet by the time this airs, but if you're both kind of building this out, do you sort of see, even in the Polygon universe, like two of these running for different purposes, potentially interconnected? Or do you picture them both connected only to the L1?
I think it's possible. I think it's too early to tell how exactly the architecture will work out, just because the stage of the development is fairly early. But I don't see why they can necessarily serve different use cases and be interconnected for specific purposes. I think all of that is possible. But again, it's very early, and I think the way we work on this is actually very collaborative. Within Polygon, we have like weekly meetings where we discuss like the things that each of us is working on. And as you mentioned, there is more than just Hermes. So like the ZK team at Polygon is fairly large at this point in time. So it's very exciting to have these conversations and basically share ideas on how like I'm trying to solve something, and somebody might have already solved it, and then if I will have some solution that somebody is trying to figure out. So it's actually been very interesting. By the way, just to kind of like, as an aside, as I was leaving Facebook, one of my concerns was that I had this really awesome team that worked, I worked together with at Facebook, and I wasn't sure what it was going to be at Polygon like, but I think so far I can say that the experience has been very similar in that where there is a lot of people who are deeply understanding crypto and zero knowledge, and, I collaborate them, almost on, I wouldn't say daily basis, but definitely like, on weekly basis. And we kind of discuss all of these things. And so this has been a very good outcome in my mind.
Do you also feel like leaving a big kind of corporate, I mean, you built Winterfell as an open source project, which is awesome, but it was within a corporate. Now you're in a crypto company, I guess we'll call it Web3 company. Yes. Do you feel like, is there more openness also with the community outside of the org, because you're in this new situation? Or do you feel like actually in Facebook, they were pretty open as well?
I think so. There are two aspects of it. There is the aspect of like working with directly with your colleagues, which I think in Facebook was pretty open. It was very, like everybody was fine with open sourcing things. It was very collaborative environment as well. And you got a lot of freedom, to be honest, as part of that research organization. And I can speak for a larger company because, I've only been exposed to like this crypto research organization within Novi, which is like part of Facebook. It's been a very open and free environment to experiment and kind of, the mandate was that we are working on future tech, so we can take this kind of experiments and figure out what...
You get to be real. Yeah, you get to do kind of like the fun stuff.
Yeah. The other aspect of it is where you need to interact with the outside world and when you need to go through kind of all the bureaucracy of the large company. That was much less kind of streamlined as it is, for example, in Polygon, because even something as simple as giving an outside interview requires a lot of approvals, even trying to publish.
I know. I remember trying to get someone on for Winterfell. I was just told, like, nah, you're going to have to go through tons of stuff. So I was like, okay, fine.
I think like one example, just to contrast, again, a larger organization like Facebook versus a smaller, kind of more nimble, I would say, organization like Polygon, is that when we wrote a blog post about Winterfell, it took about like a month and a half before we could publish it. So the blog was already written, but it had to like be approved. There was like other teams involved that needed to do this. I think within Polygon, we wrote the blog within a week, basically, and we published it. So again, like within the crypto research team, the blog was ready, but it then took another month and a half to get it published. And here it was much, much faster. And, there are objective reasons why some organizations need to be slower and get, layers of approvals. But, those are the facts.
Totally. Yeah. I mean, it has purpose. I think it's understandable why they need to do that. I don't think it's out of like maliciousness that they take longer, but it is from the outside, especially when you are just kind of trying to get some insight. It's a bit frustrating, and it sounds like you're in a little bit more of an open space now. I kind of want to keep going on that idea of like the open source tech space. So far in the Stark world, there's been one large project, Starkware, that has sort of dominated a lot of the narrative and thinking and research around Starks. Do you feel, though, like, is it time that there's going to be actually like a pretty full outside open source version of Starks coming? Do you see that sort of on the horizon?
Well, first of all, to talk about like open source Starks, I think there's been implementations already. So like even starting with like as early as even before then the Gen Stark was a kind of an open source implementation of Starks. I think there were other implementations. I think you had Remco at some point. They also worked on an open source Stark prover. And then Winterfell, for all practical purposes, it is an open source Stark prover even right now. You can use it now. Some of the aspects, it's an evolving project. It's a research project in some ways where, you probably shouldn't just use it in production just yet. But hopefully with time, it will get to the point where you can use something like Winterfell for in production if you wanted to have this custom error that describes your specific computation. I do hope that over time people will migrate more toward using VMs because it is much simpler. If you don't need to learn how the cryptography under it operates and how you need to write errors, for example, it does make it much more simple. I do think one of the, I don't want to say deficiencies, but the complexities of Starks has been that you had to learn this error thing before you could do anything useful. And I think still are very few people who understand them deeply enough to be able to write errors for sophisticated programs out there. Mm-hmm. And this is not necessarily the case. For whatever reason, maybe because it came first, maybe because it is simpler, R1CS is much better known. So it is, I don't think the deficiencies of Stark is that necessarily lacking open source implementations. I mean, there is even an open source implementation from Starkware for ETH Stark. It is that they were extremely complicated to use without they didn't have their own DSLs that were simple enough, or it basically required you to spend a lot of time on this, scaling this learning curve before you can do anything useful with them. But now, as we have, Starkware has Cairo and we're working on Miden VM, those should be much simpler. And I do think, other VMs might come around as well. Somebody could build it. But I do think that the path forward for kind of making this more accessible to developers is this type of virtual machines, which make it much easier for people to just start using them.
That's interesting. I did feel like there was a lot of mind share spent on Snarks, especially in 2019. There was this what was it, Snarktober, I think was the name, when you just had research paper after research paper coming out just around Snarks primarily, and you didn't, or I haven't felt that in the research side around Starks, except for from primarily the Stark community, which is quite small. It's been mostly around Starkware. But yeah, are you already meeting groups that are trying to get into it? And maybe with these VMs coming online, they could actually start to do something with these and use and kind of tap into the properties that Starks have that are unique.
I think for one, I see more people or more projects kind of making use of different Stark components, such as Fry, for example. There's other projects out there that are trying to rely on Fry and kind of marry, Georgie's thinking, planning to use them. There are other ones out there that I'm aware of. So I do feel like the understanding from kind of people who are very deep in ZK tech of what Starks are and how they can be used, and how different components of Stark can be married with different components of Snarks is increasing a lot, and that could lead to some interesting kind of outcomes. But I also do think that if we work hard enough and make those VMs accessible enough, people will not even need to care about what proving system I'm using, or they can they don't even need to know that the underlying proving system of Miden VM is Starks or something like that. They just know that there's zero knowledge proof generated, and then this is the properties that it has.
Totally. So going forward, I mean, you mentioned before that right now Miden is basically Distaff with the Winterfell prover architecture, but what is the future of Miden on the technical level? What do you already see on your roadmap to change?
So there are quite a few improvements that we have in mind for Miden specifically. So as I mentioned earlier, one of the things that Distaff was lacking is random access memory. So this is something that we're bringing in that will make Miden VM fully Turing complete. But there are two other things that we're trying to, or kind of working toward with Miden VM. The first one, we want to make it extremely developer friendly. So there should be no difference between, let's say, a developer writing code for Miden VM versus some other VM that is not necessarily tailored towards zero knowledge proofs. And getting a little bit into technology right now, so most of the VMs that I'm aware of that are out there, they kind of expose a lot of this, it's not necessarily cryptography, but you need to understand. So you don't work with integers within the VM, you work with, field elements, for example. And we're trying to make it so that this is not the case. You only have to, if you wanted to, you can just use 32-bit integers that the VM understands, and that's what the VM kind of natively supports. There are a few other things, but basically, the idea is that to make it almost indistinguishable from a regular VM, so there is no additional kind of overhead that you need to learn about, anything that a regular developer would not be aware of already. So that's one aspect. The other aspect, which is maybe a bit further down the road, is that we're trying to build it so that it's kind of at the core of the VM, you can support kind of privacy in the future. So as an example, most rollups right now, they're used for scalability purposes. They're not used for privacy purposes. I think there are some rollups, like from Aztec, for example, that do work for privacy purposes as well. But most rollups in their current shape are used for scalability. And this is what kind of the but the immediate goal of Miden project is as well. But we do want to make sure that there is a roadmap or clear roadmap of how you can get to, let's say, something as complex as privacy-preserving smart contracts, where it's not only that your transfers are private, like, even on other networks or in kind of privacy-preserving systems, you can provide privacy for simple transactions. But what we want to achieve is privacy at the smart contract level, where if you want to hide the code and you don't want to reveal the code of your smart contract, you can still do that. And the VM is being designed in such a way which naturally should lead to something like that. I mean, there is still a lot of questions to answer in terms of how this will work, and still be interoperable with Ethereum and all of that stuff. And this is something that we'll be solving next year. But there is a very clear understanding, like even the way the programs are defined and built is that you can hide parts of the program and reveal just the part that you want the public to know, and still generate the proof for the entire program, for example.
Yeah. I mean, you're so right, though. Like the ZK boom, in a way, came because of the scaling question, not necessarily because of the privacy question. But there are a few teams that have retained that privacy ethos, but also bringing privacy back into the models. So in your case, like you're, I guess, using these Snarks for both the ability to create a rollup, something almost to like scale a blockchain. But are you also using Snarks in that model for privacy, or do you use something else for privacy?
No, the idea would be to use Snarks as well. We will need to have the recursive Snarks to do this efficiently. So this is something also to work on. But I think with the VM model, once you have the VM, a recursive Snark is definitely possible and, should be fairly efficient. So the idea is that once we have recursive Snarks and we have this kind of foundational components that allow you to, hide different parts of the program within the VM, you will be able to support privacy-preserving smart contracts on the blockchain.
Wow. That's really exciting. I want to kind of go back just real quick to the beginning of this conversation, the Snarks versus Snarks and how they differed. Do you actually take any ideas or insight that you've learned, like that are happening in the Snark world? Or do you feel like this is completely a new path? Like the underlying builds, the kind of cryptography, the things you're using are different enough that you don't need to or you can't borrow from the Snark world?
There is some borrowing going on already. I think, for example, the changes to Miden VM that I'm working on right now, they flow directly from something that Plonk was doing earlier, this permutation-based checks. And this is a very powerful technique that in the original version of Distaff VM, it wasn't even used because I wasn't aware of how to use them. But now that these techniques, permutation-based checks, are being used widely in the kind of community, I mean, I don't want to say because I'm not sure I know the full history of how it started out, but Plonk was one of the systems that popularized it, and I think Starkware is using the same permutation-based checks in Cairo, for example, and they're very, very powerful cryptographic techniques that simplify a lot of things. So there is definitely some cross-pollination is going on. And then I think things from Stark, as I mentioned, Plonkish arithmetization is somewhat. It's not the same as Air, but it has a lot of similar ideas in it. So they're not two separate ecosystems, as I want to say. There are differences, but there is also. I feel like with time, the differences are getting more and more blurred rather than becoming more accentuated.
Yeah, I love that. It sounds amazing. I mean, I like that idea of sort of using these techniques from the different proving systems and then finding out. Like, I'm just wondering if like down the line, we'll ever be able to like mash up the acronym Snarks. Oh, God. I'm not allowed to name things.
I think there is enough invested into different namings right now that probably is not going to change that much. Well, we'll see.
Anyway, cool. Thanks, Bobbin, for coming on the show and sharing so much of this journey and actually like kind of giving us a fresh look into the Stark world, what's on the horizon. And with the project Miden, good luck with it.
Thank you so much. Thank you for having me.
I want to say thank you to the podcast producer, Tanya, the podcast editor, Henrik, and to our listeners. Thanks for listening.